area under the curve using n rectangles. This is also known as Riemann or Riemann sums. I'm not sure how to. R-I-E-M-A-N-N. I think it's Riemann.
If he's German, it's Riemann.
Yeah, I think he was German. Yeah, Riemann. What rhymes with Riemann? Riemann sum. So what we're going to do is n triangles, right? So area under a curve, remember the area under the curve of function f from a to b is the area under the graph of f and above the x-axis between x equals a and b. Now, eventually we're going to do a specific one, right? We're going to do x squared minus x plus 3 from 2 to 5. We're going to find this area. But I just wanted to kind of generalize, so here's just a little generalized diagram showing us stuff, right? So we start at A and we've got x1, x2, x3, all the way to B. So how wide are each of these guys? What's this delta x? Okay, if we're going to do n rectangles, what's the formula for delta x?
B minus A divided by n.
Yeah, b minus a, right? So we're going to take this distance, whatever this distance is, we're going to split it into n things. So we're going to go delta x is b minus a times n.
Divided by n.
Sorry, yes, divided by n. I wrote what I wrote, but I said wrong. So this, we'll call this area 1. This will be area 2, and this will be area 3. If we kept going, we'd hit area 51, but down in Nevada. Then what area is in here? So this is x sub I minus 1 and x sub I, so this is area. No, it just has a number. Xi, or area I, right? That's area. And then this would be like area n, right, at the end there. Okay. Now, what we're doing is, so we're going to use rectangles. So we've got the base, which is delta x, right? That's the change in the x. So the base is delta x. And for the height, we actually have a couple of choices, right? Like,
The one on the left.
yeah, I could use the one on the left, I could use the one on the right. So we are using the one on the right. Okay, so you will see when you look into this, if you look into this further or go on, you'll see left-handed Riemann sums and right-handed Riemann sums and in the middle Riemann sums, right? So you'll get different areas based on whether you use the left boundary or the right boundary. So here you can see we're using the right. If we use the left boundary here, then this area for 2 would be this, right? Because I'd be using the left-hand end to represent the height. So you could think, well, what if we did the left and the right and then just average them, right? I mean, that would get a little closer together, perhaps, but let's see what actually happened. All right, so wait, that's not my notes. So we know that A is equal to x0, like if we were going to give A an x thing. But instead we'll do things in terms of A. So we say, well, x1 is A plus delta x, and x2 is A plus 2 delta x's, right? So we have one change in x, or two changes in x. 3 is A plus 3 delta x. So what's x sub I? A plus I delta x, right? We need to add, if we're finding the ith term, which would be kind of a general term, right? We need to add I delta x's to it. Okay, so now we've got delta x and we've got x sub I, right? Where that's going to be the right hand, well, f of xi, right? This f of xi will be the height. So, how do we find the area of the curve 2 to 5? We leave that. We know to find a good approximation to the area by using a series of trapezoids, we're going to do it with an infinite number of infinitely small width rectangles, right? Which is basically, we know what happens when we do that, we get the actual area. So, let's find the general form for the area under any positive curve from A to B, closed interval, right? A, including A and B, using n rectangles. To determine this area, we need an expression for the area of some rectangle, the ith rectangle. So the ith rectangle's base is just delta x, right? But what's our expression for delta x? B minus A over n. So that's the base of the rectangle, and its height is the function evaluated at the right-hand edge, right? Because we're doing right-sided sum. So this one, the height we're using is f of x sub I. So the height. But we're not going to say f of x sub I, right? X sub I it's f of a plus I times delta x, but delta x is b minus a times n. So that's our height, right? So we're getting x sub I, but x sub I is a plus I delta x, which is a plus I times b minus a over n. We're just kind of substituting our way through. Now, we need to add up the sum of n rectangles of the same width, so we can use sigma. So the area under the curve using n rectangles is A is equal to the sum of I equals 1 to n of the base, okay, so that's delta x, times the height, which is f of x sub I. Okay, so we've got base times height, where delta x is b minus a over n, and x sub I is right, x sub I is a plus I delta x, or really a plus I times b minus a over n. Yeah, this is f of x sub I, but this is what x sub I is, right? So we're doing f of this.
Oh, yeah, but yeah, x. Like
Yeah.
the second part. Yeah. Instead of x sub I, it's f
Oh, it says f of x sub I.
Yeah.
Oh. Okay, so then it's f of. Wait, this says f of x sub I?
Yeah.
How did they get old stuff? Wow. It's a mixture of things. Note, the larger the number of rectangles within the interval, the smaller the width of each rectangle. So if we can make the number of rectangles infinitely large, so as n approaches infinity, then the width will get very, very small, or infinitely small, and we will have an exact value for the area under the curve. Find the exact area by summing the areas of an infinite number of rectangles of infinitely small width. So therefore, the area is the limit as n approaches infinity, the sum of I equals 1 to n of delta x times f of x. Let me guess, this says f of x on?
We also don't have that last one.
Which last one? Huh?
I give a sentence. Find the exact area by something that we don't have that one.
Oh. Wow. Okay, I guess you could write that in. A plus I times b minus a to the n.
You also forgot to close the parenthesis way up. No, way up.
Well, I forgot that one too.
Long before.
Why not point it out long before that, Jared?
Which one? That's
Right.
all. That's closed. Oh wait. Better.
Oh, thank God.
Thank God. We couldn't move on.
Changes that.
We couldn't move on until we had closure.
Yes.
Groans. Yes. All right. Moving along. And yet again, we're just going to repeat this over and over.
Just the next half hour.
Let me
of
guess.
our
This one is f of x sub I.
Actually, no, that's just x.
Is it really?
No.
Okay, so by now, we should know what delta x is. It's b minus a over n, and f of x sub I is f of a plus I times b minus a over n.
Why do we have to write that 3 times?
I don't know.
How many do you want forgetting that?
I went through it asking myself the same thing. How many times do we have to do this?
Too many?
Okay, so now we can do an actual example, right? Let's find the exact area under the curve of f of x is equal to x squared minus x plus 3, graphed right here, for x equals 2, or for on the closed interval from 2 to 5, between the x-axis and the curve. Okay, so we're looking for this area, right? And the idea is we're going to divide that into n rectangles. How wide could they be? Okay, so here's what we're going to do. You got a lot? Yeah, okay. Should be enough room. It takes a fair number of lines. So let's start off with the formula, right? So the area is the sum, the area is the limit as n approaches infinity of the sum of I goes from 1 to n of delta x times f of x sub I. Right, so the I is going to be 1 and then 2, so we're going to add f of 1, delta x times f1 plus delta x times f2, so on. Right, but infinitely. All right, so let's fill some stuff in. So the limit as n approaches infinity. All right, let's go over here. What's delta x? B minus a over n. What's b?
5 minus 2 over.
Okay, so delta x is 3 over n. So we have the sum of I equals 1 to n of 3 over n times f of x sub I, right? Which is going to be f of a 2 plus I times 3 over n. So let's just call that 3i over n. Okay? Yeah, I know. That's what you were saying. That's what I was writing. Okay. Now, we know what function f is. Right? We have a definition for function f. So that's equal to the limit as n approaches infinity of the sum of I going from 1 to n of 3 over n. Okay, so f of x says take whatever's in the brackets, square it, then subtract that thing from the squaring thing, and then what, add 3? So take whatever's in the bracket. So 2 plus 3i over n, quantity squared, plus x, right? Or sorry, minus. So then minus the quantity that's in the brackets, right? 2 plus 3i over n, and then plus 3. Okay, so we've got f of, right, and now we're doing a specific function. So really, we could have done any function from 2 to 5, and up to this point here, we're good. And now we're doing this specific function, right? So we substitute in and say, okay, what is f of x? Well, that's defined for us, so we're doing this. All right, so now, limit sum. Okay, so we're going to square that, right? We're just going to simplify what's in this set of brackets here, right? Whoops. So simplify what's in this set of brackets. So we square this. So it's first term squared, first term times the second one, times 2. So that's what, like 12? So it's 2 times 3i over n is 6i over n. Doubled is 12i over n plus 9i squared over n squared minus 2 minus 3i over n plus 3. Okay, so we squared the first set of brackets, we subtracted, the second set of brackets, we added the 3. All right, so we say, well, do we have any like terms? Yeah, we got some numbers, and we've got these two guys. So it's the limit as n approaches infinity of the sum of I equals 1 to n of 3 over n. And what do we got? Let's put these guys in order. So we've got 9i squared over n squared plus 9i over n, so 12i minus 3i, and then 4 minus 2 is 3 plus 3 is 5, plus 5. All right. Now we can do this, right? Because we did this yesterday. It's the same idea. Okay. We know what the sum of I squared, right, as I goes from 1 to n is. Okay, so here we go. We could take the 3 and stick it out front, right? It's 3 times. 3 is a constant. So it's 3 times the limit as n approaches infinity of the sum of I equals 1 to n. And now what we'll do is we'll take this n, right? So pull the 3 out there. We now have a 1 over n. We're just going to go multiply through by 1 over n. So we have 9, now I can use fancy colors, I squared over n cubed plus 9 I over n squared plus 5 over n. And so the reason I'm writing I squared and I cubed in colors is because we know we have a formula for the sum of I squared, right? It's on our formula sheet. And we have a formula for the sum of I. Okay, so it's 3 times the limit as n approaches infinity. And now we're going to drop the summation, right? Because we're going to replace the summation with the formulas for these things, right? And we can do the individual sums. It's just the sum of this plus that plus that. Okay, so carefully switching colors here. We have 9. Okay, so what's the sum of, oops, hang on. Let's put a bracket down. We got a 9, and on the bottom we got an n cubed, and then the sum of I squared is n times n plus 1 times 2n plus 1 over 6. Okay, so what the red is doing, it's replacing the I squared, right? I squared is being replaced by n times n plus 1 times 2n plus 1 over 6, and we still got the 9 and the n cubed. Plus 9 over 2n squared. And we'll use green for the sum of I, right, which is n times n plus 1. Plus 5. Right, so if we add up n 5 over n, we just get the 5, right? If you add up, if I add up 10 5 over 10s, I'm just going to get 5. So if you add up infinite 5 over n's, where each of them is infinitely small, you just get 5, right? It just sums up to that.
Well, wouldn't it be like 5 plus 2.5 plus 1
No, it's just n. Remember, n is, so let's say n was 2, right? Then I'm going to add up 5 halves plus 5 halves, right? So I go from 1 to 2. If n was 3, I got 5 thirds plus 5 thirds plus 5 thirds, which would just be 15 thirds of 5.
Okay.
If n was 4, it'd be 5 fourths plus 5 fourths plus 5 fourths. So if n is infinity, then it's 5 over, like,
Okay.
if n were a million, I'd be adding up 1,000,000 5 millionths. So we're just going to end up with a 5 here. Okay, now, where did I write this? I'm going to add a line that I don't have on here, because this is the tricky part. Here's how we're going to do this. So I'm going to throw in one more line. And I'm just going to go into one color. So, I want to divide this by n cubed, right? But I don't want to expand that. I mean, that would be like the worst thing in the world, is we've got to start expanding these things. So here's what we're going to do. We're going to say, all right, I got a 9 over a 6. Okay, so I got a 9 on the top. I got a 6 on the bottom. Hang on, I'm going to split these out a bit. So I'm going to say, let's take that first n and divide it by one of the n's, right? We've got n times n on the bottom, right, or n cubed. So this times n plus 1 over n times 2n plus 1 over n. Okay, so all I've done is take the product and split it out into individual products, right? So 9 over 6, yeah, okay. N over n. So what's on the bottom? N cubed, right? But it's split out so that I'll take each of these guys and divide them by an n. Okay, and then we'll do the same thing over here. Plus 9 over 2, and I've got an n squared, but don't make that so big. So we're going to take an n over an n times an n plus 1 over n, and then plus the 5. Okay, so here, same deal, right? Let's throw that in brackets. So I've got 2n squared, right? But I'm just splitting it out. Okay, make sense? Okay, now we can do the division.
It's not a bracket. There's one extra.
Better?
There's one extra.
Oh, it still doesn't match?
Yeah.
No. There. There. Oh. I added one I didn't.
Better safe than sorry.
Yeah, I guess. It never hurts to add too many brackets. Well, as long as they're balanced. Okay, so what have we got? So we've got 9. Okay, what's n over n? Just 1, right? Okay, it's going to be a 6 on the bottom. Now, what's n over n for this, right? This is going to be 1 plus 1 over n. Okay, so we're taking n plus 1. So n divided by n is 1. 1 divided by n is 1 over n. Times, okay, what do we got here? 2n divided by n is 2 plus 1 over n. Oops, better throw that infinity in there. Right, so next line we get to drop the n approaches infinity because we know that's going to be, and that's going to be, there'll be nothing left. Okay, so we've got a 9, so the n over n is 1, and this is 1 plus 1 over n, and a 2 on the bottom, plus 5. Extra set of brackets. Okay, so really, you don't have to do this line. I wouldn't do this line, right? But I'm just showing you. So really what I would do is just say, yeah, okay, the n here. I'm just going to divide this by n, divide this by n, divide this by n. So effectively, you're really going from here down to here. But I think it's handy to see that so you know, oh, right, that's how that happened. Okay, so that's 3 times. All right. We dropped the limit now, right? Now we can take n to infinity because there's no n's in the denominator to worry about. So we've got 9. We got a 6, so we've got a 1. And we've got a, what detail? I'm going to do this. So 1 plus 0 times 2 plus 0 plus 9 times 1 times 1 plus 0 over 2 plus 5, and yeah. Okay, so all we've done now is taken the actual limit. So as n goes to infinity, this becomes 0, this becomes 0, this becomes 0. Everything matches up. So if you're looking through it, you can say, okay, that matches with that. It's all present and accounted for. Okay, so now we can do it. So we got 9 times 1 times 1 times 2, which is 18 divided by 6. Yeah, well, let's just write 18 divided by 6. We've got 9 times 1 plus 2 is 9 over 2 plus 5, which gives us 3 times 3 plus, and you know, it's 4.5, right? Because we're going to actually multiply this. That's okay, we can multiply a half. It's not like it's... So 3, what do we got? 8, 12.5. So 37.5 square units. Square units. Or units squared. Okay, so that's the procedure. Keep that handy in front of you as you work your way through a few of them until it sort of starts to gel. Okay, this is what I have to do. Oh, any questions?
Is every question going to be that much of a bitch?